A solute dissolving in a solvent is an equilibrium process. It's actually much like the process of evaporation. Initially, we have the solute dissolving, and we don't have any recrystallization because there aren't any ions in the solution to recrystallize. But as more dissolving happens, we get more dissolved particles, then the rate of recrystallization will increase, and at some point they will become equal to each other, and we'll get a dynamic equilibrium. So we've got sodium chloride crystals dissolving into sodium chloride ions, and we also have sodium and chloride ions recrystallizing back into the solid. Starting out, we've got our sodium chloride crystal here in water, and initially there are no ions out here. So this will start to dissolve, and the water molecules will come around and form those ion dipole forces and take the ions out for a ride in the solution. And so we've got a lot of dissolving, but very little recrystallizing. So when we were talking about evaporation, we were talking about evaporation, the more energetic particles being able to escape into the gas phase. And then we were talking about condensation, which is when those gas particles rammed into the surface of the liquid and got stuck again, right? So here we've got the ions being solvated by the water and taken out for a swim. And then if they come and they bump into this crystal again, they can get stuck, right? So we've got recrystallization. As we get more and more ions out here, the rate of recrystallization increases, and at some point those will become equal. We have some qualitative terms for the concentrations of solutions. A saturated solution is one where we have the solute in dynamic equilibrium with the dissolved solute is in equilibrium with the solid solute. So that's what we were just talking about. So for a saturated solution, if you add more solute, it won't dissolve. If you think about a sponge that's saturated with water, it's full of water, right? And if you try to put more water into it, some will just run out the bottom, right? It's full, it can't take any more, it's saturated. So here the solution is going to be saturated. If the solution is unsaturated, that means there's more room for solute to dissolve, and if you add some more, it will dissolve. You can also have more solute dissolved than is possible. Wait, that's not right. Well, it's not stable, that's for sure. But we can have a supersaturated solution, and this has more than the equilibrium amount of solute. These sorts of solutions are unstable, and when they're disturbed, the excess solute will precipitate, often dramatically. So I've got a couple of videos here. There's no sound. So this is a supersaturated solution of sodium acetate. And I stuck a metal rod in there, which disturbs the solution. And what you're seeing there is solid sodium acetate crystals forming. And that's not time lapse or anything, that's in real time. It happens very, very quickly. This is sometimes called hot ice because it kind of looks like it's freezing, but it's not. And actually when this happens,
series of
I don't know why it just goes to that so quickly. We didn't want to see that one the first time. We definitely don't want to see it again now. And here's just playing around with sodium acetate. So these are supersaturated solutions. You can stick some toothpicks in there and grow these pom-poms of sodium acetate crystals. And there's a thermometer in there, so the temperature there is 52 degrees. So that's warm, right? Like it's 20 degrees in here right now. And so the solution was initially 20, 25 degrees, but then when it crystallizes, it gets warm. So it looks like it's freezing, but it's getting warm, and that's why it's sometimes called hot ice. It's really neat stuff. It's also really, not stable, and so it's not like you could go to the store and buy a jug of saturated sodium acetate.
And this is the only way to do it?
You, the way you make it is you create a saturated solution at a higher temperature, and then you let it cool down. And if you don't do it just right, it'll just crystallize on its own. And I've tried doing this before, and sometimes it's like, okay, nobody look at the solution, right? Don't think any bad thoughts about it, because that might disturb it and cause it to precipitate. So I think of it as a little bit like being, Wile E. Coyote or the Roadrunner running off a cliff, right? Do they fall immediately? No, they don't. Is that how real life works? No, cartoons are like a study in violating the laws of physics, right? Let's see how many laws of physics we can break in one cartoon. Wile E. Coyote runs off the cliff, and he doesn't start falling until he notices that he's run off the cliff, right? So this supersaturated solution is like Wile E. Coyote that ran off the cliff. It doesn't realize it shouldn't exist yet. And then you disturb it in any way, sometimes even just bumping it, or I swear, thinking about it, or being too anxious or something, just bad karma will make it start precipitating. And this will precipitate until the liquid that's left is now just a saturated solution. So supersaturated solutions are super fun. So we can make a supersaturated solution because the solubility of most solids in water increases with temperature. Here we have the solubility of these salts, and it's measured as the grams of the solute. How many grams will dissolve in 100 grams of water? And then we see the temperature range from 0 to 100 degrees. And we see that as you increase the temperature, most of these, the lines curve up. Right? They become more soluble. So, if you make a saturated solution at a high temperature and let it cool down very, very carefully, you might be able to form a supersaturated solution. Most compounds won't do this, but some, like sodium acetate, do it pretty well. Here's sodium chloride. Sodium chloride does not have much temperature dependence in its solubility, but some of these, like potassium nitrate, goes way up. And then there's a few weird ones. One example is cerium sulfate, that as you heat it up, it becomes less soluble. Because somebody always has to do it backwards, right? Mess everything up. So forming supersaturated solutions is cool, but it doesn't happen for most things. Most things, what will happen is you can make a saturated solution at an elevated temperature and let it cool down slowly, just like you're trying to make a supersaturated solution, except it's like, I know that I'm falling off the cliff, right? And so as it cools down, it will precipitate or solidify slowly. And as that happens slowly, it's crystallizing and it's dissolving again. And so it has time for that crystalline structure to reject impurities. Because like if you have table salt, it wants sodium, chloride, it wants this perfect pattern. And so if you get something like potassium in there or anything else that doesn't belong, that's going to tend to dissolve off again and get replaced. And so by recrystallizing, you can purify a substance, a solid, and you can also grow some really beautiful crystals. So this is a picture of rock candy, which is just recrystallized sugar. You can make rock candy at home, but if you want to do that, look up some instructions on how to do that. I remember trying to do this as a kid, and I didn't know what I was doing, and I just wasted a lot of sugar and ended up with sticky, wet string, right? So you have to kind of know what you're doing. But all rock candy is crystallized, recrystallized sugar. So solids are more soluble as you increase the temperature, and the effect on temperature on gases is the opposite. So solutions of gases, the solubility of gases is going to decrease with increasing temperature. And we can observe this in soda, right? So if you pour soda that's been in the refrigerator, it's cold, you'll have less foaming and less fizzing than if you pour a warm bottle of soda, right? If you have 2 cups of soda that are open, we know that they're going to go flat eventually, right? And this is something you could try at home. Pour 2 glasses of soda, put 1 in the refrigerator, and leave 1 on the counter. And come back a few hours later and taste them. The one that's on the counter, the one that's warm, is going to go flat faster than the one that's in the refrigerator, because the solubility of gases is less at higher temperatures. This is significant in aquatic life. In warm lakes and rivers, oxygen levels are lower. And so some fish need to live in cold water, other fish need to live in warm water. But they're going to die if they're in the wrong temperature of water, because the warm water doesn't have enough oxygen, and so they'll literally suffocate. This is also why you can have thermal pollution in, say, a river. You've got a factory, and they're discharging warm wastewater into the river. That water could be perfectly pure, good water, but because it's warm, being dumped into this river, it's increasing the temperature of the river, which causes oxygen levels to go down and can cause fish and other aquatic life to die. So, yeah.
This is probably like they mentioned on the Soda Stream, like carbonation milk, they say always use cold water when
Yeah.
that way it doesn't all escape at once.
Right, yeah. So if you're trying to carbonate water, you want it to be cold. And the same thing works for making root beer floats, right? Have you ever made root beer floats with root beer that's not cold? It foams all over the place. You didn't even shake it or anything. You just put a scoop of ice cream into it and go, what the heck, right? But if you use cold soda, cold root beer, you'll have a lot less problem with that. So I have people in my family that really like root beer floats.
If it's colder, so that carbonic acid just stays carbonic acid, what happens?
Well, it's that the carbon dioxide is more soluble.
Okay.
So the reason that soda is fizzy is because the carbon dioxide is coming out of solution, right? If you just have a saturated solution of carbon dioxide in water, it's not going to taste fizzy at all, because it's those bubbles that we're feeling. It's the carbon dioxide coming out. But in warm soda, it'll come out faster. Yeah. Any other questions? My question is, why do people have to stand and talk outside of my classroom? Pressure has a big effect on the solubility of gases in liquids. So if we increase the pressure of the gas above the liquid, that will increase the solubility. And this is how you can sell carbonated beverages. So you put it in a can or a sealed bottle, and you have carbon dioxide under pressure here. And so that will cause the CO2 to have a higher solubility in the water, in the soda. When you release that pressure, then the CO2 bubbles start coming out. and the soda begins going flat as soon as you open it. If you've got, say, a 2-liter bottle and you seal it up again, some of that CO2 will come out, but it will cause a certain amount of pressure to happen, so that the going flat process will stop until you open it again. Here we're looking at carbon dioxide and water in a container with a variable volume. If we take this container that's at equilibrium and we compress it, we make this volume smaller, that has effectively increased the concentration of CO2, right? It's increased the pressure of CO2. And so that will cause more CO2 to dissolve. There is still CO2 coming out of solution, but the dissolving will increase, and so we'll end up with more CO2 in the water. Of course, we can quantify this, and the equation for this is called Henry's law. It describes the relationship between the solubility of a gas, which is usually measured in moles per liter, and the partial pressure of that gas. It's the partial pressure of the gas, not the total pressure, that's going to affect the solubility. So these are related by a constant, which is called Henry's law constant. Henry's law constant is going to depend on the gas that you're looking at, the solvent that you're looking at, and the temperature. So, I mean, it's a constant, but it's kind of not really constant either. So this is a table showing Henry's law constants for several different gases. This would be in water at 25 degrees Celsius. Let's just make a note of this one, because next slide we're going to do a problem. So 1.3 times 10 to the minus third molarity per atmosphere is the Henry's law constant for oxygen and water. So this is asking us to determine the solubility. So I'm going to write this down before I forget it. Determine the solubility of oxygen and water at 25 degrees Celsius, exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So they're telling me that the partial pressure of oxygen is 0.21 atmospheres. I'm not going to use the 25 degrees in my calculation, but that is important because this constant is only valid at that temperature. I'm not going to use the 1 atmosphere because what I really need is I need the partial pressure of oxygen. So the solubility of oxygen here is equal to the Henry's law constant times the partial pressure of the oxygen. So 1.3 times 10 to the minus 3 molarity per atmosphere times 0.21 atmospheres so I'm getting 2.73 times 10 to the minus 4. The atmospheres cancel out, and so my units are moles per liter. If we're keeping track of our sig figs, this would be 2.7 times 10 to the minus 4 moles per liter. So that's how much oxygen is dissolved in water at room temperature, normal atmospheric pressure. Any questions?